When working with function operations, what we're going to learn is we're going to learn how to combine and then create composite functions. And in combining, what we're going to be doing is we're going to be working with adding and subtracting functions. So when we look at a function and I see a indicator like f plus g of x, what that is asking me to do is to add f of x plus g of x. And when I have f minus g of x, that is asking me to take f of x and subtract g of x from it. So it would look something like that, where we have f of x minus g of x, or f of x minus g of x, or understanding that f plus g of x is going to be f of x plus g of x. So as we are doing these function operations, we can go ahead and take our f of x and our g of x, and we're going to do the corresponding functions. So here we want to add it, here we want to subtract it. Okay, so as I take f minus g of x, it becomes f of x minus g of x. So I've gone ahead and substituted in the values of f of x here and the values of g of x here. And when we do our subtraction, we want to make sure that we are distributing the minus sign, the negative one, and then go ahead and do your combining like terms. And now we have 2x squared minus x plus 9. And that is your answer for f minus g of x. And as we do the addition, of course, we are going to take f of x and we are going to add g of x to it, and then when we combine like terms, we get 2x squared plus x plus 7. So there you go. That is when we were to add and subtract. And looking at our domains, and I do believe for these two functions, our domain is going to be all real numbers, because if we look at f of x or g of x individually, any number that you substitute in for x is going to give you a true value, so it should be all real numbers. And as we go into this next, where we are going to be multiplying and dividing, that is going to look a little bit more like we were talking about a composite function, where we put one function into another function. So let's see, this is the same thing. When I have, what are f times g of x? So f of g of x, or f divided by f of x divided by g of x, sorta, or f of g of f divided by g of x. So if I take and I multiply f of x times g of x, that is going to, of course, be f times g of x. That is going to be this trinomial of f of x times the binomial. And when we do that, we are going to do our distributive property and combine like terms. So when I do my distributive property, I am going to take and multiply 3x times 3x squared minus 11x minus 4, and then I'm going to take and I'm going to multiply 1 times 3x squared minus 11x minus 4. And when I do the distributive portion of this, we get 3x times 3x squared is 9x cubed. 3x minus, or times negative 11x is going to be minus 33x squared. 3x minus times minus 4 is going to be negative 12x. And then, of course, 1 times all of that becomes plus 3x squared minus 11x minus 4. When you go to combine your like terms, what can we combine? We can combine these two right here, which will give us negative 30x squared. We can combine those two right there, which is going to give us negative 23x, and then just bring down my others because there is nothing to combine them with. And there is my multiplied answer. Domain, again, is going to be all real numbers because there is nothing within those factors that gives me any limitations. And let's see, when I do my division, the division is going to be set up a little bit differently. We're going to take f of x. and we are going to divide by g of x. And I'm not sure if that is complete or not, but I may be able to do some simplification here when I factor. So again, this is, f divided by g of x, and if I quickly factor the numerator, as I factor my numerator here, I have, I'm able to factor that into 3x plus 1 times x minus 4, and when I factor, the reason we factor is so we can cancel some stuff out usually, so those two are going to become the value of 1, and then therefore my answer is going to give me just x minus 4. And there you go, there's my final answer. Domain. What would cause this to be a not true statement? Well, right here, if we look at that denominator, if x is negative 1/3, we would get 0 in the denominator, which is not possible. So in my domain, x cannot be equal to negative 1/3. That's a limitation on my domain. And as we work with composite functions here, or composing functions, we are going to take the output of one function and put it into the input of another function. So as I look at this identifier, f of g of x is how you would read that right there, f of g of x, which really means that we are going to take a value of g of x and put it into f of x, right? We're going to find this g of x value, and then we're going to put it back into f of x. So what that means is if I look at this, I have f of g of negative 3, so I want to take f of g of negative 3. So that means I'm going to find out what is g of negative 3. Well, g of negative 3 is going to be negative 3 squared, or 9. Now I'm going to take that 9 and I'm going to put it back into my f of x. My f of x is negative x minus 5, and that is going to be, which is equal to negative 9 minus 5, which is going to be equal to negative 14. And that is my composite function there, where I took the output of one function and used it as the input of another function. So let's see here, looking at this next set, it is asking me to find the f of g of negative 2. So I'm going to take g of x is equal to x minus 2, and I'm going to find g of negative 2, which I'm going to replace x with negative 2. And that tells me that g of negative 2 is going to be 4. So I'm going to find f of 4, and that is going to be f of x is equal to x squared plus 1, and then therefore f of 4 is equal to 4 squared plus 1, or 17. So the f of g of negative 2 is equal to 17. All right, now if we threw another example in here and just looked at, if I said, hey, find g of f of negative 2, and you can see that it's not f of g, it's g of f of negative 2, so I would turn around and find, looking at it, is find the g function as the input of f of negative 2. So f of negative 2 is going to be, again, I replace my x with negative 2, is going to be 5. So that output will now become part of my input for my next equation. So g of x is 5. G of 5 is going to be equal to 5 minus 2, which is therefore 3. So the g of f of negative 2 is equal to 3. So that is just another way of looking at another example of my function inputs. All right, looking at using composite functions in a scenario, a store is offering a 15% discount on all items. Also employees get 15%, or I'm sorry, also employees get a 20% employee discount, and they want you to write composite functions for the following. A is to model taking a 15% discount and then a 20% discount. So if we have d of x can be the discount, and with that we can say that e of x can be the employee discount, okay? And now what would we do from there? So if I were to take my discount, it would be, if I were to take the regular discount, it would be 100% minus 15% times whatever the price is, which is going to be the same thing as 0.85x. And then the employee discount would, of course, be 100% minus their 20% discount times whatever that item is going to be, which would be a 0.8x. And when we look at what is this thing where we're taking the discount, so I think that would be d of e of x. Nope, my bad. We probably would take, we would find the employee discount, and that would come to, I guess either way when you do this, it's going to be 0.8 times 0.85x, and then this is going to be 0.85 times 0.8x, and it turns out that both of our answers are actually going to come out to going to be the same. We're going to get 0.68 discount, or it's going to be a cost of 68% cost. Does it matter which discount you take first? It shouldn't, because in the end the cost is going to come out to be the same.